Okay, I'm gonna start now. So, hello again, everyone. Welcome back to this room, or welcome to this room if you were in a different one before. Um, yeah, in this session, we're gonna talk a bit about how we can use TensorFlow for sports analytics. Yeah, and I just want to like make one note before I start. So, if you've seen like the sports symposium, like the website, it says that I was going to talk a bit about fantasy football. So I will not actually be talking about fantasy football because like I had some reevaluation like when it came to like what we were doing in this workshop, and I want to make it easy for everyone to understand. And as such, I have made this very beginner friendly when it comes to like ML and like just TensorFlow in general. So I guess with that, I'll just start and say a few things about myself. So my name is Pranav Tavildar. I am a senior here at UConn, and I am doing a dual degree in computer science, and I'm doing an individualized major as well in data science. I'm also the president of the UConn Data Science Club, and I will give a link to join that later as a little bit of a self-promotion. But yeah, for now, I'll talk a bit about like how we can use TensorFlow to predict some NFL data. So this is just like an outline of how we're going to proceed today. A table of contents. So first I'll introduce a bit about TensorFlow, give some history, some background, talk a bit about how like it works on a lower level, explain the idea of like a neural network. We're gonna make our model, and yeah, let's just get into it. So TensorFlow. The first question is, if you've never heard of it, like what exactly is it and how can it be used? It's been thrown a lot around lately, given how there's been like an ML boom lately, given how processing is better in computers, and these algorithms allow for like very powerful things to happen. So TensorFlow is an open source deep learning library that makes creating models more easy, flexible, fast, and reproducible, which is why it's very popular in industry at the moment. But it's also very popular for other applications because it's very you can do like many things. It's like a very powerful tool that can be leveraged. And just as a bit of history around TensorFlow, so this is a product of the Google Brain team, and it was this software itself is evolved from a previous software that the Brain team was creating called Disbelief, which was they were working on it in 2011, but they turned the machine learning code that they had at the time into TensorFlow because a piece of hardware called the TPU, the Tensor Processing Unit, was released at that time. And yeah, that was like in 2015, TensorFlow was released. So, and it's been like heavily used ever since. So let's talk a bit about like the alternatives to TensorFlow and why we should use TensorFlow. So TensorFlow is often preferred by people in companies who are doing a lot of work because it's easily deployable to many servers and projects, and it's also very versatile. Some other alternatives are PyTorch and Caffe. These are two other alternatives, PyTorch being one of the more popular ones. So PyTorch is preferred by people doing research because like it's easily debuggable. There's a bit of a joke going around in the computer science ML community that like people who use PyTorch are a little bit pretentious, which is why we have this meme here saying when you're the only one of your friends who uses PyTorch instead of TensorFlow. But that's up to debate. But regardless, Cafe is also like it's not as known, but like it's also used by a lot of researchers and startups, and it has very good capabilities for small but specific fast use cases. But why should you learn TensorFlow? So I mentioned the TPU, the tensor processing unit. So the biggest advantage of TensorFlow is the idea of a tensor. So what exactly is a tensor? Tensor is just like a word for like data which has dimension. So for example, if you have a zero-dimensional tensor, that's something that's known as a scalar. I mentioned earlier in the prerequisites that a bit of linear algebra knowledge would be necessary. And this concept becomes a lot easier to understand if you understand like just the idea of how data works with dimension. So if you have a vector, that's a 1D tensor. You could also have a 2D tensor, which is a matrix. So Tensor specifically, the TPU is optimized so you can do many linear algebra operations, such as vector matrix operations, and there's a lot of gradient calculations when you're working on TensorFlow. And this is very dominant when it comes to like machine learning and deep learning. And it basically, on a low level, it leverages the structure of this GPU, the graphical processing unit, to solve powerful, very complex tensor operations. Okay, so you don't necessarily need to install TensorFlow locally, but if you would like to do it, there are a few ways to do it. So if anyone has Anaconda as a managing package management system, Anaconda is good because like it allows you to like sort of compartmentalize some things. But keep in mind, I'm going to show you an alternative where you don't need to install anything locally. But if you're interested in installing anything locally, the slides will be up, and these are the commands that you have to run to install these things. But yeah, let's talk a bit about what TensorFlow is and like what the components are. I talked a bit about the tensor processing unit, but let's see how that like sort of works. So initially, TensorFlow was composed of these different concepts, which I'll elaborate a bit further with an example. But you know, you have the operations, as I mentioned earlier. There's a lot of linear algebra involved when you're actually doing some low-level TensorFlow encoding, and for that reason, you have like many different packages which is optimized to work with the hardware. There are also nodes, which are two different types of variables known as constants and variables. Constants, as the name implies, are constant, and variables, the difference is that while you have to declare it with a value in the beginning, you can change those values. But think of it as like relearning sort of another programming language in this sense, where if you understand these concepts, then you can like sort of create like neural networks from scratch. And then there's something called a session, which provides the flow in the TensorFlow. We talked about tensors, so how does it flow? But it's not used anymore in version 2, and I'll get to that soon. Okay, so this might be a bit difficult to get your head around, so I will illustrate it through an example to show how it works. How many of you have played this game at any point in your lifetime? Just raise your hand. Yeah, it's a pipe game, right? So this is a perfect way to describe how TensorFlow works. So as I mentioned earlier, the nodes hold the data, right? They're just like they're like the bones of the skeleton in a sense. And you know how you can like move these pipes around? Like I think the objective of for those who haven't played this game, I should have mentioned that first. But the objective is to get the pipes flowing to the output, and you have like a bunch of pipes, and if you click on them, I'm pretty sure they like turn. And if you click on these pipes, they turn, like they rotate, and that should like basically you're trying to redirect the water flow. So imagine this valve is closed shut. That's what we're beginning first. So TensorFlow 1, how it works is that imagine these hold the data, but the data set is coming from the session object, and it's traveling through the nodes, and it's being transformed by the operations. The operations being the connections between the pipes and like just the way that you can turn the pipes. And this whole structure is called a graph. So the way TensorFlow 1 used to work is that you used to have like all of these structures, but you need to have like the flow chart basically set before you can actually feed in any data. And this is good like when it comes to like deploying your model, right? Because you don't want a machine learning model like breaking on you like when it's actually in production. But you know, like when you're debugging it, it makes it a bit difficult to work with. And we'll explore how that works. And that's because TensorFlow version 2 uses something called eager execution. So when I found out about this, I was like, like this guy up here. Because like the eager execution is a very interesting concept that like helps simplify these things. So this is the workflow for TensorFlow 1, right? You have the nodes, you set them up first, you put the operations in place, you make a graph structure, and then you start a session. And that's how you get the data in. And then that's when the data comes in. On the other hand, version 2 Tensor eager execution, basically what it does, it allows you to do it piece by piece, in the sense that you can flow in the data and you can work with the data as it's being pushed through the system. So let's take a look at it. So if you go to the Sports Analytics Symposium website, you find a link to my GitHub repo, and you want to open this file first to just show like how eager execution works and how it's different. So I'm going to ask a very hard question now. Can anyone tell me what 1 plus 2 is? 5. Close. 3. Someone said 3. So yeah, that's correct. So this is we're using TensorFlow 2 on this bottom cell, and we'll show that first. And here, see, it says that we have a tensor that has the value 3 here. I'm not sure. Let me maximize this so that it's easier to see. Can everyone see this? I'll write something on this. It's called a TF1 v TF2. It's in code. It's in the code folder. I don't know how to zoom in on this. Oh, okay, there we go. Okay, so it prints out 3, but let me show you what you had to do beforehand. Beforehand, we're gonna use something where we disable our eager execution, and we're gonna see what happens now. Okay, so what does everyone think will happen this time? Does anyone have any ideas? I have an idea. Like, so as we expected it earlier, I would assume that like since we have 2 constants with the values 1 and 2, we'd get 3, but alas, we don't. We just get an empty tensor. So the reason why, remember how I talked about earlier, you had to have your graph in place before you start flowing in your data. So you used to need to have this. So like in order to do this, you'd have to actually run it with a session object, and then you can get the last line. You can get like the answer that we're expecting, which is 3. And I'll show that here. See, we have 3 now. But like it's so much code for something that we could have done like very easily here. So which is why personally I prefer TensorFlow 2 for development. But some defenders of TensorFlow 1 will be like, oh, but you lose the speed and the precision like when you move to TensorFlow 1 because you have easier execution. It takes more time for the model to work. Well, to those haters, I have something to say. There's something called the tf.function method, and that basically gives you all the benefits of TensorFlow 1 with TensorFlow 2. So this is some very low level stuff. You might be wondering, how can we make our computers like think like humans using all of this stuff? And to show you how to do that, I'm going to make you all make your own neural networks from scratch. No, I'm joking. Like, fortunately, there's a lot of research in this field. And in order to make our neural networks, like we're going to use a lot of APIs, which are prominent in TensorFlow 2, because we're going to use a lot of APIs that are prominent in TensorFlow use 2 from the Keras API, which handles a lot of stuff for us. And I'll just give you a big an overview of what we're going to do. How are we going to make our code think like a human? Oh, also, these are just some common matrix multiplication and operations that you could be using if you want to do stuff from scratch. But we're not doing that. So, learning, machine learning, that's a very commonly used buzzword, but it's very simple in concept when you think about it, because basically all we're doing, we look at ourselves inside. We think about how we as people, in order to actually implement these things, because that's what all machine learning is based on. So has anyone here ever taken any P&B courses? Cool. So basically there's an actual thing in your brain called neurons and like their systems of neurons, right? Yes. So like in the scope of the workshop, we're going to be covering ANNs, which are known as artificial neural networks, which is not it's called artificial because it's not like an organic neural network that is known in your brain, but it's something where we can make the machine itself mimic a brain in that sense. So we start with the idea of a neuron, right? So approach it like a black box with an input and output. Like people tend to complicate this a lot, but in essence, that's all you have right now. You put stuff in, you get stuff out. So I'll explain a bit more in detail what that actually refers to. So we have different parts of it. We have the node itself, right? So that'll have like a bias value in itself. And there are also weights which connect different nodes. So you might have seen like the diagrams, right, with circles and like lines connecting them. That's basically what this is. I'm sorry, guys. But also we have like something called an activation function. So let's say that, so that basically determines how the neuron will fire. So as I mentioned earlier, this is how neurons in the brain work. So let's say we have two nodes, right, that are feeding in data to this big circle node over here. So I'll just explain what's happening. So that connection between the input node into this node is connected by something called weights, right? So we have a weight of 1 here from this node, and we have a weight of 2 from this input node. So basically, you would take the data, you would multiply it by the weight, right? And then you would add the bias, and you'd put it through an activation function, which basically is a function which you can use to determine like what the output of the node will be. So there are different types of activation functions, which I will cover a bit later. But in essence, this is all a neuron is. So the thing is, for neural networks, right, you just stack like a lot of these together so that you have so that you have like essentially a network, right? And that's what this looks like. So there are 3 different types of layers in our networks. We have input layers, hidden layers, and output layers. So input layers and output layers, they're only one of each. As I mentioned earlier, like think about the black box, right? You put stuff in, stuff comes out. But the thing is, in between, you have like these hidden layer nodes, which basically do perform a lot of computations and and it adjusts itself, which is why it's so different from other machine learning. Like it's why it's different from other things that we do in programming when we're programming systems, because it has the ability to reflect on itself and like change its weights based on like the feedback it's getting and like the results it's getting. So you can have multiple hidden layers, but in essence, the only layer that you can directly affect is the input layer by deciding like what sort of data you want to pass through that. And I mentioned earlier, right? The training, it's basically, I mentioned that the neural network reflects on its performance. And it does that through a concept known as back propagation. So forward propagation is basically what I mentioned right now, where you feed the data through this thing, it gets transformed by the hidden layer neurons, and then it gives out an output. But back propagation is when you see the output and you compare it to what the actual score is, because you're trying to predict something, right? But what if that prediction is wrong? And if it's wrong, then it will go back and it will try to improve the accuracy. So the difference between the actual score that you're getting and the expected score, that's something called loss. It's also called cost in some disciplines, but I will call loss for this lecture. And basically, to determine, you want to minimize loss, right? Because you want your neural network to make something that's as close as possible to the real like data itself, because you're creating a system that predicts well. And that is done through a method called gradient descent. So there's this formula over here, and if you're like very well versed in statistics, you may be able to understand it. But I'll just like explain it in plain words so that it's a bit easier to grasp. So you have a feedback cycle, right? You have this beta hat t+1, which is going to be the new weight. And you basically take it by taking the old weight and descending down. You basically find the derivative or the gradient of the loss I wrote lost function, but it's actually loss function, so keep that in mind. But you want to find like the minimum, right? Because you want to find the point like where when do we no longer have more loss? We want to make that number as low as possible, and the best way to do that is to find the minimum using calculus. Now, fortunately, you don't have to actually implement this because this has been implemented and it's optimized essentially. And we can basically go take a look into that code ourselves. So the Sports Analytics Symposium. Okay, also a high chew for whoever gets this question right. So I know this is a baseball snack, but sports, right? So who's this coach? Does anyone know? Just raise your hand. Yes? Yes. I need to do some learning myself to prove my throwing. But don't worry, there will be many more opportunities to get these high chews. You'll see that shortly. Okay, but as I mentioned, right, you're using prediction models in order to do this. You're trying to predict data. So does anyone know what play-by-play analysis is? Yes, do you want to mention it? Mhm.
What time it is.
Exactly. And like all of that data is somehow publicly available due to web scraping if you took the last course, or like by a bunch of officials who released these reports. So I got my data from NFL Savant. So basically what I'm saying is in a CSV, I have every single play that was done in the 2021 to 2022 season. And if you want to find it out, they have it for like every year, but I'm just going to be using one season for this model. And let's try to create a model that predicts whether the next play is going to be a first down, given some data that we have beforehand. So in order to see this data, you have to go into the GitHub again, and you want to open the Python notebook file that's called UCSAS 2022, and I'll explain it. So remember earlier I mentioned you don't have to download it locally. If you already have TensorFlow, good for you. You can do that on your machine, but just to keep some results constant, I'm going to be doing this on something called Google Colab, which is Google's cloud-based uh, IPYNB like file system. Because like the results you get are much more consistent, and you just get some good stuff. So let's start by importing pandas. Now you might be wondering, this isn't a pandas workshop, this is a TensorFlow workshop. So why am I using this? So one of the most important steps when you're working on creating a model is you have to have good data. Remember how I said earlier, neural networks is just you put stuff in, stuff comes out. There's a very common phrase that is used for this thing. It's called garbage in, garbage out. So you don't want to put garbage in and get garbage out, right? So you want to have some good data and you want to have it clean. So even though this was scraped, right, we see a lot of problems here. Does anyone want to notice like anything? So this function basically just shows the first 10 values of the data frame that we have. So we're basically just taking the Python, like the data that we have. This is the play-by-play data from NFL Savant, and this is what it looks like. Oh wait, let me run this from scratch. So I need to import the. It's going to give me an error because I need to import the CSV file. So let me just show you how to do that on Google Colab really quickly. So you basically just have to do file. You wanna go navigate yourself to here. You want to click this button. If you haven't git cloned this on your local machine already, I recommend you do that. But if you don't have it now, you can just do it later. So don't worry too much about it. But let me just find the, yes, here it is. Okay. So we're gonna upload the play-by-play notebook. And yeah, it says uploaded files will get deleted when this runtime is recycled. So every time you start a new runtime, you have to upload it, which is maybe why you'd want to like do this with like an older, like with your own laptop as well. But for our purposes, it's fine. Okay, so here we have a lot of NaN, or like not a number of values, right? That's one of the problems that we have, because like if the data frame sees these values, it's not going to know what to do with it. So we have to find some way to handle those values. And the way to see how many not a number values there are is by using this method. Wait, let me just forward so you can see this a bit better. Can everyone see this a bit better now? Okay. Yeah, sorry about that earlier. Okay, but yeah, this column takes this command takes every single column in the data frame and tells you how many NaN values there are. And here we can see an offensive team, defensive team. There are a lot of NaN values. There's also something called unnamed, right? So that's because when you get it from NFL Savant, for some reason they have like empty columns. So we can't just have that, right? Because that spoils a lot of things. And then like also it doesn't give us any useful information. So basically what I'm saying is we got to drop it like it's hot. My boom. But yeah, so this is how we're gonna do it. So we're gonna think about what we need. So firstly, let's drop some empty rows, like empty columns rather. And yeah, so this basically this command drops those empty columns. So that's good. We don't have those anymore. Then we want to get rid of rows where there's no play occurring, because they have some no play occurring rows, but that's not something that we need for our model. It's going to be irrelevant, and like honestly, it's the source of a lot of NaNs that we have here. So I think that it's good if we get rid of that. For the analysis we want to do, maybe if you want to do some different analysis, you'd want to handle this differently, but we don't need it, so we're getting rid of it. So similarly, we have offensive. We're getting rid of rows where there's no teams playing, because sometimes in no play like that misses. Sometimes you miss some stuff, and like I remember when I was looking back at the values, there was still a lot of NaN. So, yeah, we got rid of those rows as well. And if we look at this, we will get some different values. And also, there's one more thing we want to do. So, there were a lot of features. You remember seeing a lot of those, right? So I was thinking about which ones are the most relevant to the question we want to solve, right? What's the chance of getting a first down? And I felt like these values, like the quarter that's being played, the minute, the second, who's the offensive team, who's the defensive team, the current down, how many yards to go until the next down, the yard line, and the series first down is the value we're trying to see, because that is basically saying if it's a 1, that means that that means you successfully got a first down. If not, then it's going to be a 0. There's also formation, right? Because that I feel matters like a lot. There's also like play type, whether there was a sack, there was an interception or a fumble, because I feel like those things are all like very important to think. Well, I mean, all of this stuff is pretty much important, and I think the other ones are just a bit intuitive. So I'll just leave it like that. So basically what we're going to do is we're going to trim our data. So we're going to get rid of all the other rows, because a lot of the other rows has data that we don't want to work with, because it's either has too many non-number values or it's not really relevant. So what that is up to you when you're deciding your model, but since I'm making this model, we're following my rules. So we're going to keep these values. So this is how you keep these values. And how does our data look now? We're going to look at the not a numbers and look at that. We have a value in every field. So this is good. So there's something called data pre-processing that we need to do. Well, let me just make sure I ran this. Oh. It's no play. Oh yeah, because I ran it once. Notebooks can be a bit annoying sometimes. I'm just gonna write it like that again. Okay, see. And that works. So now we have some categorical variables, right? But one of the problems is TensorFlow, since it's based on a lot of computations, doesn't handle written data well. So how are we going to change our written data, right? The way to do that is something called encoding. You have to process your data before you can feed it into the neural network in order for it to work. So one thing we can do is called one-hot encoding. So let's say we have like a bunch of formations, right? Like I can think of a few on my hands. Like, well, firstly here, I should have asked this like much earlier, but how many of you are like familiar with football to an extent? Okay, that's a good amount. Yeah, but formations is like how the team basically prepares themselves to get to the next down, right? Like there's some positions, some popular ones are shotgun, there's no huddle, there's yes, yes, thank you. But yeah, those are some popular formations, right? So let's say we have shotgun, right? Basically, one hot encoding is if we had a row where I could just show you the information actually. So let me get you to the place. Yeah, we have under center shotgun, right? So um, I said text is a problem, right? So one thing we can do is we can just create a different row for every different type of formation there is. And if that is the formation the team is going with, you make it a 1. If it's not, then it's a 0. So that's a very simple way to encode it. So so we're gonna do that for like some of these things. So out of all the values we have over here, we have some categorical values, and we're gonna do that with formation and yard line direction. So in order to do that, you do something called pt.getDummies. So if you're familiar with statistics, this is an idea of like making dummy variables. That's basically all one hot encoding is. So that's what we're going to do. This chars function allows us to do that this pandas function, sorry, allows us to do that pretty easily. And we're also going to do that for yard line direction. And this axis 1 just means it's going to be like a row, right? So we're going to change these. We're going to make these one hot encoded. We're going to join them together into a data frame. We're going to drop the original rows and we're just going to add it back. So how will that look? So these are our like plays that we have here. Firstly, I should mention that, and these are the yard line directions. So we changed some things, right? So every time there's a dummy, right? So like if we're going with a field goal formation, then it's going to be a 1 for field goal, yada yada yada. It's going to keep going like that. But yeah. So, but can anyone see a problem with this? I'm gonna move up so there are no spoilers. But can anyone see a problem with like creating a new category every time there's something different? Yes? Yes, there can be so many columns, right? And like, especially given that this is a lot of matrix multiplication. Since this is a matrix multiplication, this is going to be very, well, actually here, pick candy. I'm going to throw this, hopefully you catch it this time, or, nice catch! You should be in the NFL, you could be doing some data science about you. But anyways, um, yeah, so yeah, you're right. Since you're doing a lot of complex multiplications, you want to reduce the number of columns you have because like if you have too many columns, then just your processes will take a long time. So one way to deal with this is something called count frequency encoding, which isn't very popular because it has some disadvantages, but for our purposes, I think it should be fine. But basically, what it works is that it just finds the frequency that some the category is repeated, right? So, question: does anyone know how many teams there are in the NFL? Correct, correct. Well, a lot of people knew that. But see, we have like a category called offensive team and defensive team. So if we were gonna we need to make 32 categories for each of those. So instead, another thing we could do is just like we can find the frequency using this is unique method, and we can find how often they're used, and we can do this with play type as well because I feel like there are a lot of those as well. So you want to like basically it's just like a frequency list, right? So you have every time like let's say New England Patriots shows up, you add 1 count to that. And this way, the reason why you're doing this is so that you don't have any biases, because technically you could just assign some arbitrary number. But remember earlier when I was talking about weights, yeah, that you could lead to some problems there. So this is one way to balance it. But one of the problems if you pre-process like this is that sometimes you might have some values with the same weights, but I think for our purposes, they're statistically similar enough that like our model still works. But yeah, this is basically, we're just count frequency encoding everything here. Okay, now we're gonna train. Now we're gonna actually start using this, doing some machine learning. So how machine learning models work is that you have to split the data set into a training set and a testing set. So the testing is going to be for later when you want to verify how accurate your model is. And the training set is for like actually getting that. Remember I was talking about backpropagation, gradient descent? That's done with the training model. So there's another popular package called sklearn.model selection, and there's a method called train test split. And that's basically what we're going to be using because it does it easy and neatly for us. So basically, we're going to split it in half, which is why we have test size over here. We have a value for the x variable and the y variable. So does anyone know what the y variable is without looking at the thing? Okay, everyone's looking at the thing, so it doesn't matter. Yeah, but like we're looking for how likely is it that are we going to get a next? Our model is going to determine if we're going to get a first down for the next play. So that's going to be our y variable. All of the other categories that we've kept in are going to be our x variable. So that's going to be our input nodes, essentially, the x variables, and we're going to have one output node, which is the y variable. And yeah, we're just splitting it 50-50. So we're just going to use this method over here to make sure that it is 50-50. And we're just going to do that by looking at the shapes. So yeah, okay, this is technically one more, but that's because like it's an odd number. You can't really do much about that. But yeah, so we're just processing the data for training. Also, another thing is that you want a lot of the data to be very similar. So you do something called like standardizing it, where you transform the data in order to make sure that it's in a specific range that you want. I'm sorry, I'm going a bit faster right now, but we're running a bit shorter on time, so I'm going to try to get this done. But as we see here, we scaled, and let me just run all of this. We scaled our data here, and it looks right? Because like all of a sudden we have much more close values to what we wanted. And yeah, so our pre-processing is done. Now we're going to create our neural network. So this is a bit arbitrary, but we have some things that are decided beforehand. So a sigmoid function is a specific type of activation function, which basically determines whether it's like logistic in the sense that you can get a 1 or a 0, and it's basically to determine that. So this will be our output layer, and this will determine like how this will basically give a binary output. And we also have ReLU, which is a very popular function as well for the layers in between. So it's just going to do some computations on that end. And we have one binary output node. So we have to specify a loss function, right? Because how are we going to calculate the loss? And since we have one categorical output, we want to use binary cross entropy to determine the loss. And because that's a very good model for like the purpose that we're looking for. And here, basically, we're just defining some things where we're just looking for some metrics, right, which can help us analyze this data set. Some things being true positives, actual results, true positives, predicted results, and we have recall, which is like the ratio of all true values to the total. So we're going to be using these to do some metrics later, and we're determining this by we're going to see this happen in real time. This is going to take some time, so I have something fun planned while we're doing this. But yeah, let's just have it run if no one has any questions right now. Okay, so this is going to run. This is going to take some time because epochs basically means like it's running, it's doing backpropagation once, right? So we're going to do it 100 times. Okay, so now I'm going to put the sports in the Sports Analytics Symposium. So we're going to do a little bit of trivia. So if you raise your hand and get the answer right, then I'm just going to throw a candy at you. So let's see how this works. Okay, so first question: which team won the first Super Bowl in 1967? Yes. Correct. Okay. Second question: which team has the most Super Bowl wins? Yes.
Is it New England?
Yes. Second question: which team has the most Super Bowl appearances? Yes. No worries. Okay, which team is known as America's team? How's this going? Yes? Yes, correct. I'm getting better for a second. Yeah, right now we're on our 30-30 part. Okay, so we have a lot of time. I'm just rushing through this. Okay. So, which city did the Rams originally play? Like from the beginning? Yes. Wrong actually. From the first game. Yes. No. No, but no. It's Cleveland. Between this. Okay. So which teams use this? What are the two teams that use the same stadium for home games? Yes. Yes, but which teams use that? I'll give it to you. The Giants and Giants. Also, follow. Yeah. Okay, what are the follow-up questions? Who won? What? Where is MetLife Stadium located? Yes. Yes. Correct. Not like that.
We're going tomorrow, are you coming? We're going tomorrow to game.
Oh, really? Didn't know that. Who won the Super Bowl in 2016 when Tensorflow was 4 months old? In 2016 it was the Broncos.
Oh, I had to try. They have the most.
Oh, no question. Okay, next question. How many points is a touchdown worth? Correct. Who is the only player to be rated all-star in baseball and football? Correct. Inventor of the Bull Burger. Okay. Which team had completely undefeated season? I think yes, I heard you say it first. Sorry. Okay. Who's the coach of the New England Patriots?
You'll go with that.
Correct. Oh, they're done? Okay, that's it, everyone. Why can't this company did it? Okay, so the epochs are done, right? So we have a loss here. It's sort of stagnated here, but there's a better way we can see this data. And we're going to do that using Matplotlib. And we're gonna plot those metrics that we were talking about a bit earlier as well. So here, what we can notice is that we do get some accuracy, but it starts stagnating, right? So this indicates that maybe we ran it too long. Maybe I did that on purpose so I could do this event, but who knows, right? It could just be a data quality problem. But so theoretically it could be improved, but we reached a pretty good accuracy as it was. So we could just leave it like that for now. But if you're interested, there are some functions that we can go over, but we don't have the time for that at the moment. So, so now the question is, how do we actually do the predictions, right? Because that's what I was talking about this whole time. It helps predict. So the way we do this is we take our skilled X values and we can feed them in to the model. And by using this model.predict function, we will get what we want. So is there something strange about this output? Yes. Yes. And that might seem strange at the beginning, right? Because like, why are so many of them here? Is something going wrong with the model? So, but also consider one thing, right? Like, how frequent is like someone getting a first down on any play? Like this rule requires some like football knowledge, I guess, but it's not super easy to do, right? It's like it takes a few downs, it takes some tries. So that's why it shows up like this. And so that's why it's an important thing to have like some domain knowledge whenever you're doing some sort of data science problem. But yeah, so this is what our data looks like. And we're just going to use this evaluate model to just test the loss, accuracy, and precision and recall on our on our testing set, right? Because so far we've only been using our training. But now we're going to actually use remember that half of the data we've stored aside for seeing how good our model is? Because basically, like let's say that training, let me just illustrate it simply. So let's say that I'm with someone, right, who knows what a bagel and a donut is, but I've never seen a bagel and a donut before. And that person who knows what it is will like show me, quiz me, and ask me like if they'll show me like a picture of a bagel or a donut, right? And they'll ask me what it is. but they will know what it is beforehand. So if I say it right, then like I'll know that okay, donuts look a bit more like this or bagels look a bit more like this. But if I get it wrong, then I'll take some knowledge beforehand. So that's what training is like, right? Testing is like if you just give some other data to me and then like I determine it myself. Like before, basically, essentially, it's like you're going from a controlled environment to something where you're using like real data, in a sense. Okay, so this part has been done. We have a loss of this much. We have this accuracy 70.6%, which might sound like not great, but like honestly, that's a pretty good accuracy for like most models. We can tinker it and like probably make it a bit better, but like for our purposes, I think that's pretty good. If you get like 3/4 of a chance of getting the first down right, then I think that that's a pretty good percentage. We also have precision and recall. It's pretty precise. The recall could have been improved a bit, but still be. Okay, so this is something called a confusion matrix, which proves that a bit more. So just how this is a diagram how confusion matrix works. So remember how we have like a binary output, right? It's right or it's basically we're saying that it's successful or it's not successful, 1 or 0. So it could either be true or false, and this is basically how it works. So we have true positives over here, which is when we said that yes, first time is successful, and this is how we predict it. And then there's this one where we have like it's not successful and it was true. But we also like sometimes we get it wrong, right? So we can see how it worked here. Here we have a lot of true positives, a good amount of true negatives. So we also have some errors here, like where we have like false positives, but we also have some false negatives. But I feel like if you look at the proportions, that's still pretty good. And here we just have some more information about accuracy. And yeah, these are just sort of some of our final outputs. And this is just a way where you can save your model for later. So because like maybe let's say you want to use it again. So this is how you do it in Google Colab specifically, because remember, it's not your own computer, you're using like cloud computing. But this exclamation mark indicates that you're doing like some console commands, like or terminal like commands rather, to do the things. So like you're creating a directory for the save model, you're saving it there. And basically for Google Colab, you can only take up files instead of folders, but models are saved as folders. So you need to turn it into a zip. And then if you have your model, if you load it, then all you have to do is use this simple command over here. And yeah, that's how we do this part. So if there are any big takeaways from this, where did it go? There it is. If there are any big takeaways from this, remember, data engineering is a big part. Drop values in order to get empty, redundant, or outlying influential points. Encode categorical data using techniques like one-hot encoding, or the other one that we use, the frequency-based one. Normalize your data before you use it, and when you analyze it, if you're using something where it's like a classification problem, use the sigmoid activation function, right? Because we have an output layer for one node, and we're using binary cross entropy as a loss function, and watch out for overfitting. But yeah, that's the main thing. Thank you for listening. This is just some shameless promo here. As I mentioned earlier, I'm the president of the Data Science Club. That's Hari, who's the vice president. He just presented as well. So if you're interested in joining our club, if you're a UConn student, then you can join our UContact over there. We also have a Discord server where we just like have a very fun community that talks about data science and like what's going on at UConn. But if that's all, like I'll open up the floor to questions. But thank you for your time listening. Sorry for coming over.
So maybe hidden layers.
I use 3 hidden layers. Good question. Specifically, yeah, 3 hidden layers because like I felt like that much computation was a good amount. But like generally, people use them anywhere from like 3 to 5 for like most processing problems. But like keep in mind, the more hidden layers you add, the longer the computation takes. Now let me just show you the layers so that I can specifically say that. It's a lot of epochs. Yeah, we have 3 hidden layers here. Thank you. Yeah, I think this is also time. So if you have anywhere else to go, then feel free to do that. But yes. Thank you. Thank you. Yes. Okay, that's a good question. So like, if I can be honest, I sort of did it randomly for this point because just like for the hidden layers, it doesn't matter too much. But there's like a formula that people suggest where you let me see if I can find it in my thing. I think it's probably in the images. But yeah, this is the equation. So they suggest that if you use the number of input neurons, this equation will give you like a good amount of neurons for the hidden layers. Okay, then. Thank you, everybody, for your time. Have a good day.